Okay, for mechanics today, we're going to look at three situations with inclined planes. Now, inclined planes, I'm talking about when you have situations where you have a block, a little bit like this, and typically there is a particle. I like drawing my particles as boxes sat on it, and we have to do things like make force diagrams and equations and so on. Okay, so they're actually quite similar after a while. We're going to just go through starting right at the beginning so you can get an idea of how to write your equations, because once you can do that, it's much easier. So we have a block of mass m on a smooth, so there's no friction, smooth incline at an angle. Okay, there's no external forces. That's it. So just a block sitting on a slope. Okay, couple of things to start with. Because it's sort of an inclined plane, there's the idea that, it's a bit like a table. Yeah, it's sort of like a table, but at an angle. So what does that do? What do you get when you have a block sat on a table? You get a normal reaction. You get the surface stopping something from going through it. So we're going to draw R, and R is our normal reaction. Okay, if you have a table like that, the normal reaction would be like this. If you just sort of started taking this thing and you started turning it, if you started turning it at an angle, so something like that, the arrow would sort of follow it around slightly, slightly to the left like that. So that's the idea. What else? Well, if we remember roughed, which is our trick to remember the forces: weight, resistance, reaction, friction, tension, thrust. Weight of the block is actually going to act straight down. When we draw weight, we always draw weight straight down for A-level mechanics. So we're going to draw it like this, and here it's called, the mass is m, so we're going to call it mg. Now, if it had a mass of, say, 3 kilograms, we would write 3g. But because it's m kilograms, we're going to say mg. So quite common to see mg written. Anything else we need to do? Well, it has a weight, it has a sort of a reaction. Resistance, well, there's no sort of resistance in the question or through friction. There's no tension because there's no strings or pulleys or anything like that, and there's no thrust, there's no external force. So this is the most basic diagram that you could have. Now, let's just talk a little bit more to explain why this diagram is saying that the thing should start moving or should start accelerating downwards. But the problem is we can't really do that because of the way that our diagram's drawn. So what we're going to do is we're going to zoom in a little bit here, and I'm going to draw a vector triangle of the forces making up mg. Now, the trick here, and you can prove this with similar triangles and stuff, it's not too hard, but whatever this angle is here, it's always the same as this angle here. Okay? And this lets us turn this mg into being split up, being resolved by these parts here, and that's typically more useful for us on a mechanics question. How do you find out what this thing's called? Well, it's a right angle triangle, yeah? Imagine you have a right angle triangle and an angle there, and you know what this is, and somebody's asking you this one. Well, if you started by saying cos angle, that would give you a way to describe this situation. It's the adjacent side, which is my question mark here, over the hypotenuse, which is the side that you've got. So if you rearrange this, you can describe this adjacent side. So this adjacent side is what? It's always the cos side, yeah? So I'm going to rewrite this now then as mg cos theta, okay? That's describing sort of the force going like this instead of this, because this is just not going to be that useful when it's written like that normally. It makes sense to break it up. The other one, the one that's opposite, you can do the same kind of trick and you will get mg sine theta. So when I resolve my forces, I like to get rid of the old ones, and I've got something like this. Now, a typical next step, and you're going to see this in the examples that we do further ahead, is that you then make equations about sort of perpendicular to the block. So sort of any forces that are sort of acting like this would be perpendicular, and you make equations about those. And then you take anything that's parallel. So anything that looked like this, these sorts of things would be parallel, and you make equations about those. That's the way that you can answer the vast majority of these questions. So I like to call perpendicular and parallel, and we find out the resultant force. Now, what happens when you find out the resultant force? You can use it to make F equals ma equations. So let's have a go at that. So what equations can I make about the forces in a perpendicular way? Well, if we use a different color, so R is fitting with that direction, so it's perpendicular. So is this new one that I've just done, this mg cos theta. So these are forces that would feature in an equation about what's happening with the forces in a perpendicular way. We can go one more and we can say we don't expect the normal reaction to be bigger than this, because that would mean that it would start floating, it would start lifting away. So we don't expect that to be true. We also don't expect the opposite, that it will start sinking in, that it will start traveling into the plane. We expect that they'll be equal, don't we? So R is in fact equal to mg cos theta. Or another way you can write that is you could say that the resultant force is 0. Okay, and you will find that this will be sort of, well, either actually, these will be very useful equations. Let's have a go describing what's going on in a parallel sense. I'm going to use orange for this one here. So in a parallel sense, what's going on? Well, although I've drawn it over here, this is still talking about what's going on with the block. Okay, so I'm very much interested in this one here, mg sine theta, and in fact that's the only force that's going on parallel to the block. So there is just sort of an mg sine theta. There's nothing holding it back, okay? It doesn't react with the other forces. This is the F, if you like, in F equals ma. This is the whole thing. And what I could do, because this is typically the one that's very useful for F equals ma, is I could set it equal to m and a that I don't know. And in a question, I could work lots of stuff out. I'd also get lots and lots of credit for everything that you can see here on the screen. Now, let's have a go at a slightly more complicated one. But I want you just to kind of pay attention to how much it has in common with this, which is the most basic situation. So a block of mass m on an inclined plane of theta, there is friction. Let mu be the coefficient of friction. The block either remains in equilibrium or slides. We'll talk about that in a second. Let's have a go at drawing it. So let's do our forces, and this time we're going to jump straight into, we're going to have the green as being our perpendicular forces, and we're going to have orange as our parallel. We're going to draw all the forces and we're going to break them down into one of these. So let's draw R or N or something, the normal reaction, because again, do you remember this is like a table? This is sort of pushing the block back is the idea. The mass is mg again, so I'm going to draw a large arrow that just says mg. I'm going to remember that my right angle triangle is going to look like this. Takes a bit of practice, but if you draw it correctly, it should only be about the parts that you're interested in. This here will be mg cos theta. This will be mg sine theta. Now, weight, reaction, resistance, friction, tension, thrust. Weight is there, reaction is there. Resistance, well, there is a resistance in the form of a friction. So let's have a go at drawing friction. And friction is harder to draw than you first think it is. Friction is going to act against the way that it wants to move. So where does this block currently want to move? Well, these are just balancing each other out. This is just sort of stopping the block from floating away or something. What else is left in the question now that we've resolved this? It's actually this bit here. So that is the force that makes the block really want to accelerate down the slope. So friction is then going to act against that. So we're going to draw it as this. Okay, so friction's acting up the slope. This doesn't mean that the block's going to start moving up the slope. Okay, it's just there because it's sort of saying that it's countering or it's trying to counter. It might be losing. We don't know. We need more information. It's trying to counter the way that that's going. So let's make a couple of equations. R is in fact, yes, equal to mg cos theta. They're the only perpendicular perpendicular forces in the question. And here, I don't know, okay? I simply do not know from the information if this is enough to overpower the friction or not. Okay, so these are the forces, though, that are going on in the parallel sense. I'll just give you one example. So let's pretend that the block was moving down or was about to move down. If it were the case, what would we do? Well, we could make our equation, our leading force, our driving force, take away the force against would be equal to ma. So you can make your equation of motion something like that. Notice what's interesting about when you have friction is this R is the same as the R from up here. So that's the way that lots and lots of questions go. Now we'll have a go at just one more situation. So we've done our most basic situation. We've done our basic situation, but now with friction. And finally, we're going to have another external force. So let's start drawing it. A block of mass m, so here we go, mg, and the angle is theta. So it will be theta in there. We were doing green and orange. So after a while, you are sort of on autopilot with certain elements of this. This will be mg cos theta. This will be mg sine theta. I've now broken that up. So when I break up the forces and I don't need them, I like to get rid of them. Let's read it. A block of mass m on a rough plane. Rough is a signal word for there is friction. The coefficient's mu. Okay. There is an external force as well. Okay, there's lots of stuff going on here. There's an external force F acting up the plane. So F, what does F look like? F looks something like that. Or I often like to draw them so that the ends of the arrows are on the part and going, or something like that. Okay, so they've called that just F. That's how you would kind of draw it as part of the diagram. Notice it's very, very hard for me to place mu r because I don't have enough information. Based on these forces here, this could be a really big force, couldn't it? Which would massively overpower this. If that happened, it would start accelerating up. Or what else could happen? This could be a really, really big force, and this could be a really, really small force. So then the thing would want to go down. So I don't know which direction this is going to go. So for the purposes of this question, I'm going to add a bit more information on. So I'm going to say the block is on the point. This is a phrase you'll hear a lot. The block is on the point of going up the slope. So what does this phrase mean? It means that this one here, this is a relatively strong force and it's about to start going this way. Yeah, the block wants to go this way. So now I have enough information to place the friction. Friction always goes against the direction that it's moving or that it wants to move. So I would now have to draw friction acting against. Okay, and that's how I could make my diagram. So notice for perpendicular, r is equal to mg cos theta, which is a result we've seen many, many times. It is possible to have other bits and pieces, but you need other forces acting at an angle to get them. And for the orange, for the parallel, the orange, there's quite a lot going on. Now, I'd need more information if I want to start doing like F equals ma with accelerations and so on. But I could make an equation now from what's going on. It's on the point. So on the point means that it's balanced, but it enables me to draw the directions. So what forces are going up? F is going up in the dominant direction. And mu r is acting against, and mg sine theta are acting against. And I would say that the resultant force there is zero because it's actually not moving. It's just very close to moving. So that's how we could kind of make our equations. I hope you found there, if you are quite methodical and you break your forces up, perpendicular and parallel, that it's not too hard to get started on identifying the right forces. After this, it's a case of getting some more information and using F equals ma, or sometimes, you do just solve with equalities like we've seen so far.